All right, let's get started. We are finishing today the chapter on carboxylic acid derivatives, which encompass the acyl halides, the anhydrides, the esters, and the amides. And so we started talking about what amides can do. The sections are all organized the same. We have nomenclature, followed by hydrolysis, followed by reaction with alcohol, followed by reaction with amines, and then organometallics, and then hydrides. And if there are special reactions for that function, they come at the very end. So for some of these functional groups, we omitted some of the options because they either don't work or they're not commonly used. So the ones that you see are the ones that are to use. And so for the amides, we finished up by a special type of reactivity of the amides, which was really an extension of enolate reactivity, which we did on the last slide on Tuesday, where we showed that we can deprotonate on the left and on the right. And the right side, the amine side, is more acidic, quite a bit, 8 pK units. So deprotonation occurs first on this side to make the so-called amidate ion. And you have to block here with alkyl groups and the like before the base will switch to the other side. In both cases, the amidate anion is a strong base, so the restrictions for alkylation, SN2 versus E2, apply. So then today we're going to continue with a special reaction which is rather unique only for the amides, and it only applies to primary amides. That is, amides that have 2 hydrogens left over on the nitrogen. Okay? And this is called the Hofmann rearrangement, named after this man here, Professor Hofmann, a German chemist who lived at the end of, he lived in the 19th century. And as many, in fact, of the chemists that you've seen involving the early carbonyl chemistry were chemists around the early 20th century. And many of them German, because the German school at the time was prime. So what he discovered, and this was very likely an attempt to see whether you can do an alpha halogenation of an amide using the standard conditions that one could use using base. In other words, a base-catalyzed alpha halogenation of the type that we have seen for aldehydes and ketones. Okay? And when he did that, out came an amine. And lo and behold, that amine was 1 carbon shorter than the starting amide. And as it turns out, the carbonyl that's separating the R group and the amine group winds up in carbon dioxide. So this is a really spectacular transformation, just staring at it without thinking about a mechanism, because you are basically chain shortening an amide chain. Okay, so this is a way to, if you have an extra carbon somewhere in your synthetic sequence and you want to get rid of it, this is one way to do it. If you have an appropriate function at the end of the chain, and at the moment it can be, I think, any function, because you know how to convert them all into a carboxylic acid, and then you make the amide, and then you treat them with basic halogen, that can be chlorine or bromine in the aqueous conditions, and you cut out 1 carbon, and you still maintain a function at the end, which is the amine function. So here's an example. This is nonan-amide, so it's a 9-carbon chain, a chlorine sodium hydroxide, 66% of octanamine, okay, and carbon dioxide. So how does that go? That's a more intricate mechanism, which I won't hold you responsible for, so this definitely won't show up. But a part of it, certainly the first 2 steps, you could have predicted. If I'd asked you, guess, make an educated guess of how this should go, you would have done exactly this. You know that if you have an amide, the NH is more acidic than any potential alpha hydrogen over here, so with base, there will be deprotonation at the amine side. And the way that Hofmann ran this reaction was really using equilibrating conditions, because he used hydroxide. Hydroxide is not capable of shifting the equilibrium that is set up here between amide and amidate to the right. Okay, so we have a classic situation again where we're using equilibrating conditions. We're accessing a higher energy species, but if you were to stare at this by NMR, all you would see is this species here. Okay? But the point is that you're making small concentrations of this in equilibrium with starting material, and in the presence of halogen, it gets trapped. So this is identical to what we did when we did the base-catalyzed halogenation of aldehydes and ketones. We set up enolate equilibrium, here it's amidate, and we trapped the anion with the halogen. Okay? And so this is straightforward SN2-like halogenation, and that gives you as you would have expected, the alpha halide, except that it's not a carbon, it's a nitrogen. Okay? Very much like the reaction, the base-catalyzed alpha halogenation of aldehydes and ketones, the product of such a monohalogenation is now more reactive than the starting material, so it doesn't stop. And remember, in the case of aldehydes and ketones, it didn't stop until all the alpha sites had been halogenated, because all the subsequent intermediates are more reactive than their precursors. And so they just they mop up all the hydrogens that are potentially acidic and turn this into the corresponding product. So in this case, the same thing happens. This X group activates this proton relative to this proton here. So immediately, as soon as this is formed, hydroxide pulls off another halogen. So actually, the first 3 steps you could have predicted. What happens next is a little bit more difficult to fathom, because it involves the disconnection of this R group from this carbonyl, and this is the key step in order to kick out this carbonyl as carbon dioxide. And so what happens actually is this group migrates to nitrogen. And so we have in this species, again, a classic push-pull scenario. So it's reminiscent of some of the other push-pull mechanisms that we've written, starting in Chapter 9 with neopentyl alcohol and acid undergoing an alkyl shift. We have a leaving group pulling on the right, and we have a relatively electron-rich system, in this case helped by the fact that there are 2 lone pairs on this nitrogen that can kick in this way, and so the R group migrates over here. So in that way, they trade places. So that helps. And so the R group migrates over here and kicks out the leaving group. And what you get is this piece here, which is called an isocyanate. Perhaps the closest analogy to this, to write it again, not quite the same, but it's reminiscent of the oxidation step of the hydroboration oxidation of alkenes, where in the last step we had attack by hydroperoxide on the borane, and this is a borate, so that's electron rich, and it's this negative charge that kicks out this guy, and hydroxide is leaving. You may remember that. So this is reminiscent of this kind of process. So this isocyanate would be stable in organic solvent in the absence of moisture, but it's moisture sensitive. It hydrolyzes. And if you stare at this long enough, you actually recognize why it should hydrolyze. It's actually an imine analog of carbon dioxide. Okay, so this is what gives rise to carbon dioxide. If you think of this as just an imine and ignore the fact that it's a weird imine, not with two alkyl groups hanging off, but there's a double bond on the other side to oxygen to make the CO double bond. This guy reacts exactly like an imine, and it hydrolyzes by the usual mechanism. Water adds to this carbon, proton to this carbon. That gives you this as an intermediate, and this intermediate turns out to be unstable. It's also a rather weird species. It's a species in which on the left it looks like an amide, and on the right it looks like a carboxylic acid. These guys are called carbamic acids. And these guys are actually analogs. They are the amide analogs of carbonic acid. And carbonic acid is very much in the news actually lately, including a paper by my colleague and friend Rich Sakeley, who some of you may have had in Chem 1. Carbonic acid is nothing else but the hydrate of carbon dioxide. And this is a very important equilibrium in all of your sodas. So you'll have swallowed this equilibrium countless times. Okay? Carbon dioxide is dissolved in water, but it reacts to some extent with water to make the corresponding carbonic acid, which then is in rapid equilibrium with carbonate, hydrogen carbonate. So it dissociates rapidly. And all of this gives rise to the fact that carbon dioxide only slowly evolves from your soda pop. Okay? So this is the amine analog, and it decomposes to carbon dioxide exactly the same way, except that instead of forming water from carbonic acid, you get the corresponding amine. Okay? So that's where the amine comes from. So again, I won't test for that, but we'll revisit isocyanates actually in the last chapter because they are sometimes used for doing peptide chemistry. We'll learn a little bit about that at the very end. Okay, so much for amides. And after amides, what comes next? And so then there are nitriles. Nitriles they don't look directly like carboxylic acid derivatives because there's no CO double bond, but they are clustered with carboxylic acid derivatives because all of the chemistry is related to that of carboxylic acids. You can view nitriles with a CN triple bond as anhydrous amides, where you have removed water, H2O, from a primary amide. That's one way to think about it. And in fact, they're related to amides by hydrolysis, as we'll see in a minute. So let's start first by looking at the naming of these guys. So what you do is you take the name of the alkanoic acid and you turn it into alkane nitrile. Perhaps a better way to think about it is to take the alkane stem, which we've usually done, and you just add the word nitrile to indicate that the end group is not a CH3 but a CN triple bond. And the carbon that's part of the nitrile is part of the longer chain, of course. Okay? So this smallest nitrile that one can think of is ethane nitrile. The smaller one that you might imagine would be HCN, and that's hydrogen cyanide. Okay? So that doesn't count. So we start with ethane nitrile. There's a common name for this, acetonitrile. Acetonitrile is a common solvent, cheap solvent that is used in industry and in the lab and so forth. So it's like it's a polar solvent. It's a nitrogen analog of, say, acetone. Okay? Except it's got a CN triple bond. Then you have with 3 carbons, this would then be propane nitrile. 4 carbons is butane nitrile. By definition, the nitrile carbon is carbon 1. Counting is easy because the nitrile group can only be at the terminus of a chain. And then there's branching. And so in this particular case, there is a methyl group at the 3 position, so this is 3-methyl butane nitrile. Cyclic systems are called cycloalkane carbonitriles. That's related to cyclic aldehydes, which are called cycloalkane carbaldehydes, or cyclic carboxylic acids, which are called cycloalkane carboxylic acids, and the like. So these are called cycloalkane carbonitriles. And so here's one example, a cyano group on a 6-membered ring on cyclohexane carbonitrile. Here's a molecular model just to remind you of the fact that while we're always writing cyclohexane as a flat stencil, it's actually a chair. And in this case, the substituent, of course, prefers to be equatorial rather than axial. The benzene derivative should be called benzene carbonitrile, like this generic name, but benzonitrile is accepted by IUPAC. And that's also a large volume commodity in industry. And if you want to refer to the CN triple bond individually, you call it the cyano group. We've done that frequently before. It becomes a substituent if there is a higher priority function in a chain, such as the carboxylic acid. But remember, I told you I won't give you an exam question in which we are juxtaposing 2 different carboxylic acid functions. So it's either nitrile or it isn't. Okay? And so if you see a CN group in an exam question for naming, it will be a nitrile. Okay? There's no competition. I won't set that up. Okay, so what do nitriles look like? Well, you can view them as nitrogen analogs of acetylenes. There's a triple bond, and you get the typical fixture of a triple bond. It's actually basically 2 orthogonal double bonds. Okay? So the pi systems are orthogonal to each other, and so one of them forms one pi bond, the other one forms a second pi bond. And unlike alkynes, where this would be carbon, which would mean that there's another substituent over here, nitrogen is trivalent, and so there's no substituent, and there's just a lone pair. Okay? And that lone pair just sticks out in space. It's an sp hybridized lone pair, meaning, as we shall see, it's relatively inaccessible relative to an amine, which is a lone pair sitting in an sp3 hybrid. So sp hybrid means a lot more s character, and therefore, although this is not shown accurately in this cartoon, the electron density in this orbital is sitting much closer to the nitrogen because it has more s character. Remember, the s orbital is just a ball, okay, around the nucleus. And on top of that, we have a p orbital, so we're mixing the 2. So the p orbital, unlike an sp3 orbital, it doesn't extend as far out in space as the sp, meaning that nitrogen is relatively electron withdrawing, and this electron pair is less available, making this less acidic. In the end, it doesn't make any difference because it still gets protonated. It's just a little bit more difficult. And we'll do that in a minute when we discuss the mechanism of hydrolysis. But the other aspect of this is that nitrogen, of course, as usual, is more electronegative than carbon, so it pulls. And when it's connected to carbon, this is not unlike a carbonyl group where it's an oxygen that pulls. Part of the accentuated delta plus, delta minus is the fact that there is a pi bond that connects the 2. A pi bond, the electrons are relatively less strongly held. and they're more deformable. That's one way to think about it in very simple terms. And so they distort more easily towards the electronegative oxygen. Here we have 2 pi bonds, and so there's distortion of this electron cloud towards the nitrogen is reasonably pronounced, and that's shown very nicely in the electrostatic potential map, making this carbon quite blue, meaning it acidifies the adjacent protons, and more importantly, it's subject to nucleophilic attack. Okay. So as we shall see in a minute, a hydroxide, for example, can attack there, and that's part of the mechanism of hydrolysis when we use base. So here we are, nitriles are acidic and basic, so the alpha position is relatively acidic. When you look at the actual numbers, pKa is 25. So they're about as acidic as esters. Okay? One number to remember and throw in to our sequence. So I can remind you of that. Carboxylic acids, pKa 5. We shall learn, probably next week, that ammonium is about 10. But then we know that water and alcohols is about 15. And aldehydes and ketones are about 20. So always increments of 5. That's a good ladder to remember. Esters are 25, and it turns out nitriles are about that. And amides are 30. They're the worst. Okay. And so one can deprotonate. pKa 25 is perfectly acidic enough to be deprotonated by a really strong base. Our default base is always LDA. Sterically hindered, therefore not nucleophilic, and it's very, very basic. pKa of diisopropylamine is around 36. Okay? So we're way higher than 25. So the equilibrium is shifted 10 to the 11 to the right when you deprotonate with LDA, roughly speaking. And in turn, of course, the lone pair can be protonated, but poorly so. But on protonation, you get this species, and there is some stabilization by resonance, although this resonance form is a sextet. But it's a resonance form that is useful to drive home the fact that protonation activates the nitrile even more than it is already activated towards nucleophilic attack at this carbon. And so any acid-catalyzed reaction, just like all the acid-catalyzed reactions of carboxylic acid derivatives that occur by protonation on oxygen, on nitriles, they always occur by protonation on nitrogen first. And again, it's the old story. This is a lousy equilibrium. The pKa of this guy is actually -5. So if you were to make this in a pot, which has been done using some what's called superacids, then it would be as acidic as concentrated sulfuric acid. Okay? So it's a bad camper. But you don't care. You don't want to isolate it. All you want to set up an equilibrium if you couple it to subsequent chemistry. So let's look at the chemistry. And again, the first reaction that we'll do is hydrolysis. A reaction actually that we've already mentioned previously, but we didn't talk about the mechanism. So to give you some added variety for examples that we have here, we can use this dinitrile, hexane dinitrile. The common name is adiponitrile. And I'm using this on purpose because we'll see this guy, adipo derivatives, later. Actually, the next chapter. But on hydrolysis, it gives this guy, which is hexane dioic acid, basically quantitative. Common name is adipic acid. It's an industrial compound. We'll revisit that. So this example we also talked about. One can utilize nitrile hydrolysis in a scheme that makes alpha-hydroxycarboxylic acids. So always think about systems like this as potentially being derived from the hydroxycyanides, which are nothing else but the HCN adducts to the carbonyl function. And that's a useful function. So in general ways, retrosynthetically, you can always link the carboxylic acid now to a nitrile. And the nitrile you can make, of course, by SN2 reaction on a haloalkane. And haloalkanes ultimately can be derived in principle by radical halogenation of hydrocarbons. Of course, always bearing in mind mechanisms, namely not the tertiary position of a hydrocarbon is more reactive than secondary, more reactive than primary, more reactive than methyl, and so on. But if things are right, then indeed you can go through a sequence like that. And we know now a lot of carboxylic acid chemistry to take this further. So let's look at the mechanism, and let's look at there's an acid-catalyzed mechanism and a base-catalyzed mechanism, and I'm going to do the acid-catalyzed mechanism on the board. And as will transpire, it's a scheme that actually hydrolyzes the nitrile first to the corresponding amide. So it adds water, and that gives the amide. And then we are in the amide stage, and we already know how to hydrolyze amides by addition-elimination chemistry. So the way this goes is, in the acid-catalyzed process, the lone pair, as usual, attacks the proton. We've just seen that. So we get this species, for which we can write the other resonance form, which shows you that this carbon is now extremely nucleophilic, and so it can be trapped by water. To give this beast here. And then we lose a proton. Since this is an aqueous solution, of course, we never have free proton. It's the surrounding electron pairs that pick up that proton with water. You make H3O+, but we write it as -H+ to avoid clutter. And then we get an interesting species that looks like this. Now let's stare at this guy for a little while. And you recognize that this is nothing else but the imine form of a carboxylic acid. The carbonyl function has been turned into an imine as an intermediate. And this guy turns out to be thermodynamically much less stable than the tautomer, namely the hydrogen-shifted isomer, where this proton shifts from this oxygen to this nitrogen to generate the CO double bond.